So good morning. Welcome to our next lecture in the direction of representation learning. So we will try to cover a little bit of generative modeling. So it's a very broad topic, but we will try to see variational autoencoders, and hopefully maybe together with the lab and with the seminars, we will work through details so that we would kind of understand the variational autoencoders to all details. And today, this is our goal, to go towards variational autoencoders, and then to also look a little bit at the connection. So you can have variational autoencoders, then maybe hierarchical variational autoencoders, and then we will look at the connection, how this relates to the diffusion models a little bit. Yeah, so that's the idea, and maybe also it is useful, maybe not necessary, but rather useful before discussing variational autoencoders to look at just what is autoencoders. To understand. So today we're gonna have lots of equations related to these variational autoencoders, but hopefully there are enough of these illustrative images so that you could follow through, and that then some details I think we will work through with the practicals. So for autoencoders, the underlying kind of motivation or goals was that, so suppose you don't have any training labels, what we can learn, how we can learn from just a collection of images or from a big collection of data. Now we have many tools, right? So there are different options with this self-supervised we discussed, and then but this has developed earlier on, and the idea was, okay, so let's learn to compress the data, essentially. So then if we learn how to compress the data and we achieve some high compression rates, then that means we have learned some useful encoding which captures the most essential information about the data, and maybe it even this encoding is even extracts the very relevant and good features from the data. So then to learn such encoding, then the idea was to having the data to construct this encoder and decoder, to having the data to try to learn to represent this data in a much lower dimensional space. So that's the compression part, such that it can be still well reconstructed back. So we have then two mappings, the encoder mapping that takes the data and puts it in this latent space, and the decoder mapping which sort of tries to reconstruct from this latent representation exactly the data as we had it. And so the reconstruction loss could be different depending on the context, but most commonly it's maybe the just Euclidean distance between the input image and the reconstructed image, or maybe the squared norm here. Well, if the image is a binary, it could be some like binary cross entropy or something. And then what we want to do, so then the learning is that we want to learn parameters of these two mappings, such as this to minimize this reconstruction loss. And that has found some features. So it had found some usage, like these latent representations, that they could be used as features for some other tasks, like learning a classifier or something. It was used also at some point as unsupervised pre-training. If you have a very deep neural network, we discussed in the beginning of the course that training of that is rather difficult, and you need to be careful with initialization and with your choice of activation functions, and maybe normalizations will help. So before this was before this pass was established, one approach was, okay, we could just pre-train the first layer as a variational autoencoder, and then maybe add one more layer also trained as a variational autoencoder. So just adding layers one at a time, but at every time training it as a, sorry, not variational, just a plain autoencoder, right? And then the network where we have added these multiple layers by pre-training a layer at a time as an autoencoder, then this network was fine-tuned, and then it was working well for some tasks. Also, quite interestingly, this has been used for things like anomaly detection or out of the distribution detection. One possible way to do this is that you could you take the input image, you encode it, and you decode it. And if the decoded image is very different from the original input image, then maybe it is not from our data distribution. So this is maybe this scheme with this compression or sort of the idea that we could represent the data and reconstruct it back almost without loss of accuracy is conceptually corresponds to the picture that you think of the data as maybe the data is high dimensional, like some movement or the image, but it really lies on a lower dimensional manifold. So there is some kind of lower dimensional manifold. So you can describe this data by sort of simple coordinates on that manifold. So it has low dimensional representation, but when you observe it, so you observe the points in 2D, and maybe with a little bit of noise. So this is some data around that manifold, and then like the encoder-decoder could possibly project on this manifold. So the encoder would take a point and find the reconstruction which is on the manifold, and then the decoder would reconstruct this point. If we put the data which is kind of out of the distribution away from the manifold, then the reconstruction is going to be this projection. So and then it will be far from this input data, and then we could recognize that it's not in our data manifold. So something like this. Now, there has been a couple of variants of this, and let me go through this noteworthy variants of these autoencoders. One variant is the noisy autoencoders, where you say, okay, we just gonna perturb the input with a noise here artificially. So not only that take our collection of input images, but even perturb each input. And the goal is to reconstruct the clean image. So the noisy image is fed into this encoder-decoder, but we want to reconstruct the clean image. So it facilitates this idea that, okay, so that you want to perform this projection. So whatever the noise added to our data samples, that you want to reconstruct the clean image, that's remove the noise component. And yeah, you want to interpret it as a projection on the data manifold. There was a variant of that where you replace noise, adding the Gaussian noise to the input. You replace it by kind of adversarially perturbing the input image, but just finding the maximum perturbation, which with a bounded amount of distortion, such that it kind of adversarially corrupts our loss, and then we want to minimize this expectation of this in our encoder-decoder. so as to be robust to adversarial perturbations. And then this has also some advantages, like being even more robust to all kinds of noises or all kinds of distortions. And there was also a variant called contracting autoencoder, which is adding a penalty on the encoder, on the gradient of the encoder. So what this enforces is that it says around our data points we want that the gradient of the encoder would be small, so the encoding would not change if we change the input by much. So all of these three variants, they are kind of going towards this similar goal, that representations should be robust to something, to noises, to small changes around the input data points. And that's sort of desirable property. This is what we would want it, and so you could enforce this through changing this formulation a little bit. And if you apply one of these variants, it also makes that the desirable effect that latent space becomes more smooth, in the sense that the similar codes, so if some codes in this latent representation are nearby, then they correspond, so the images that we reconstruct from them are also somehow similar and are on this manifold, so reasonable images. I ran the example to see how this autoencoders train and how the interpolation looks like in the latent space. So this is what we did. So we train like the noising autoencoder, and then we look at in the noise space we have latent codes for image 1 and image 2, and then sort of let's reconstruct all the images on the line between the Z1 and Z2. And this is what it shows. So we are kind of interpolating between. So Z1 is the encoding of 3, and the Z2 is encoding of 8. And the codes in between, if we decode them, we obtain these different variants of the digit, which we could argue it is better than interpolating in the image space, but probably not still powerful enough to do maybe more sophisticated geometric transforms or some interpolation between more complex objects. And like I tried this denoising and contractive, and they look quite similar, although they take different passes, right? And this what they reconstruct in between. If you take some code and in between, they reconstruct somewhat different things expectedly. But they look, yeah, at some point there is kind of strange transition. But anyway, so many of these images look reasonably, and so there is this smoothness. So this is to illustrate the property that we wanted for like our Lund representations when we discussed the metric cloning. So we discussed, okay, we want the points to represent the images, but also the distances to be meaningful, and so that we could like argue what is the closest representation to a point, or we could interpolate in this space. So we do want to have this representation with this smoothness property that nearby latent codes represent similar objects, and with some kind of metric in this space. And yet, by these formulations, there is nothing ensures that in this formulation that this latent space is truly continuous. It could be like, here was some image. There could be some gaps in this manifold. It could be like in this latent representation. It could be maybe some images can be interpolated and like close together, but maybe encodings of some other images, they lie somewhere else, like completely in different clusters. So there would be some gap in between, and then you cannot, like what you will construct out of this will be some image, but maybe it's not a good image. So there is no principled way how this smoothness is imposed, or compactness of this latent space should be somehow imposed, or we would like to, so that there would be no these gaps in between. And there is also no clear way how we can use these latent representations if you want to generate digits like from our training distribution. So this is good for kind of representation in some sense, but if you wanted to generate, to replace our training distribution by a generator, so if you wanted to synthesize new images, there is no kind of clear way how we could do this. Yes, we can interpolate. Yes, we can take a random point in this latent space, but it's not gonna have any guarantees in terms of whether we approximate our training distribution or not, the data distribution. So so now the relational autoencoders will help in resolving these limitations, but okay, maybe they will come with some other limitations. Before we go into relational autoencoders, let's look, so we need kind of recall some background on what is callback-library divergence. Sorry for hurrying a little bit. Do you want to ask something about autoencoders? No? Okay, so then to this callback-library divergence. It has two forms for the continuous and discrete variables. Sometimes I will switch between the continuous and discrete. For discrete, it's easier to write different expressions and kind of easier to read, but it's fully analogous. Why do we talk about this? So we need to measure the kind of discrepancy between two distributions. So if you have one distribution, and the distributions have to be given by density function. So if you have one distribution like this, and some other distribution like that, we need some good measure how to tell how these two distributions are different. Because what we're going to talk about is that learning generative models, so that, let's say, our target distribution are these images, is this y distribution, so this we want to learn, and our model distribution is this red one, and then to learn a generative model means that the generative model must produce the same distribution as our data distribution. Yeah, in fact, we don't have this data distribution in terms of the density. We will have only some points, right? So some samples from this white with higher density where there are this, okay. So we will have only these samples, but imagine for a moment that we have the density, and then one way to measure the divergence between these two distributions, or the difference between these two distributions, is this callback-library divergence. So it is this formula, and it has some like notable useful property for us. So first, it's truly a divergence, that it's non-negative. So despite we are here have this ratio of logarithm of the ratios of the densities, this could go positive or negative. But this total sum, this expectation, is always non-negative, and it's zero if and only if these two distributions are equal. And so that's the properties of any divergence. So it is a divergence in that sense. But also maybe one property to be aware of is that this is obviously not symmetric. So if we swap P and Q, then we will have a different number, but still, like, it will be, the swap divergence will be zero again if and only if the distributions are the same. So both divergence P from Q, so sorry, Q from P and P from Q, they are both divergences, but different, right? And so they will distinguish them. So this will be called forward divergence, and this will be called reverse. But of course, it depends on the context, which one is which, depending on the meaning of what is P and Q. So if P is our kind of target distribution, so this will be P, and the Q is our distribution that we are fitting to the target distribution, then this one will be forward and the other one reverse. And notably, what is very good and very useful about this divergence, it does not depend on the change of variables. So suppose I stretch this space. If if you stretch the space, the distribution, the density function should scale also. You should not only just stretch the scale density function, but it must integrate to 1, so it should be also reduced proportionally by the constant. And if you do this non-linearly, in principle, we could transform any density function to any other density function. So maybe you know this from the example that if you have uniform distribution, then if you send it through the function, so if you send it through inverse CDF, you will get the distribution with that corresponding CDF. Okay, what does it mean? So okay, so if this is so let's say sigmoid to -1, the inverse logistic sigmoid function, then we will have the logistic distribution. Right, so nonlinearly transforming densities changes them a lot and their shapes. And like this property here says that actually this Kullback divergence does not change if you change if you map the coordinates for both P and Q. Yeah, it's not hard to see. So basically, this change of variables formulas for the density, you need to look up what changes and how, and then things are canceling in this expression, and the expectation works. So it's not hard to verify, but not our goal today to look at that. What the other important property for us is that we say that this Kullback divergence is non-negative. And it is worth looking at the proof of this, because in the proof of this, there is the same, the core inequality occurs, which is used in all of this evidence lower bound, variational and inference. In all of these places, there is this same inequality is used, and it can be already seen in the non-negativity of KL divergence. So what happens? We want to show that this expression is non-negative, despite the logarithm can be negative sometimes. And how do we do this? So we define this ratio, let this ratio to be denoted as just y of x. And so we have the inequality like this, logarithm of y of x. And what we observe about this inequality is that it is, so p of x is the distributions, and this is sum over this distribution. So it's like convex combinations of logarithm of y's at different points x. And the picture for this is that we have this logarithm function, and we have maybe multiple points on this, so the whole distribution of points, but let's say just 2 points. And at one point we evaluate logarithm of y1, and at the other point we evaluate logarithm of y2. And the convex combination of logarithms is sort of here, right? So this is on this line. But this logarithm is a concave function, and so it must lie above this chord, above this line. And so the logarithm of this convex combination is above here. So this is the Jensen's inequality for concave function. So sorry, concave logarithm is concave. So we have this inequality due to the concavity of logarithm. That's called Jensen's inequality. And after applying this inequality, we just substitute what was in this y, and we see that it is logarithm of the expectation. No, yeah. So the total mass of y, and if it was a distribution, this is 1. So then the result is 0. So that we proved non-negativity of Kleibel divergence. Now about this asymmetry property, we have these nice illustrations. So suppose our target distribution is this P, and it's bimodal. And suppose we want to fit it with a Gaussian distribution. If we consider this forward Kleibel divergence, so this divergence from Q to P, it looks like this. Then the best approximation looks like this. Because here the expectation is over P, we want to approximate this distance in the log densities well on average over the P distribution. So wherever the mass of P is high, we want kind of this approximation to be accurate. And so the Q, our approximation distribution, Q tries to cover all of the mass of the distribution P better. So it stretches over this mass of P. Whereas if you consider the reverse divergence from P to Q, then it is computed in average over Q, but Q is varied. And then so it happens that this Q, which can be varied, it could kind of sort of focus on only one of the modes of our target distribution. And here on average over Q, things are fine. And here the mass of Q is 0. So and actually we don't care about missing, like to approximate this part of the target distribution. We only like, okay, so here it cannot match this mode because it's constrained to integrate to 1, right? So it must be like it must have a higher densities around this mode. So it is not the optimal solution if the distribution would be unconstrained. But if it is constrained to Gaussian, then the optimal solution is sort of could be often like finding a mode of the target distribution and approximating only that. So this is like something to consider, and this has effect in practice in different scenarios, especially when we will in practice be considering such Gaussian approximations. Okay, so this is kind of background, and now we are ready to talk about generative models. Yeah, so we say that the goal and the idea, what we want is to, if you have some target data, we would like to learn a model such that we could sample from that model data that follows the same distribution as the one is now a training set. So we assume there is some underlying true distribution, right? But it's only accessible to us through the training samples. And the approach that many or most of generative models are taken is to say that, okay, we will represent the generator as a sort of composition of really to generate something, it must be random, right? So we do need some source of randomness somewhere somewhere in this generative process. And just like one conceptual scheme that is general and flexible enough is to do the following. So assume there is some fixed noise distribution in our latent space, and then we're gonna map this distribution non-linearly into the image space. And if this mapping is called decoder, if this mapping is general enough, then we should be able to represent any distribution in our target space. Yeah, so the one example of that is like this, right? So we have some fixed distribution, we map it through the inverse CDF, we obtain some other distribution. So if this is a parametric function that we are learning, it could be it could learn an arbitrary 1D distribution. Another example that you know is with normal distribution. So if you have a normal distribution with mean mu and covariance matrix sigma, right? So you could represent this distribution as, so you could generate X as you take the mean plus, what's that, square root of covariance matrix epsilon, where epsilon is standardly distributed. Right, so in this picture it would mean, okay, so here we assume some fixed normal distribution, standard normal distribution, and then we just linearly map it to our target space, and then this could generate, right, so this could learn such skewed Gaussian distributions. But here we allow it to be, of course, nonlinear and even discontinuous, so it could kind of have multiple modes and so on. Yeah, the question is how to learn such a mapping, right? So yeah, we can say that it's general enough and we could represent any distribution in this way, but how do we learn it? And there are multiple ways how to learn this. Conceptually, we need to have some way of telling, okay, given these samples, yeah. In this latent space. Actually, there has been a paper on the topic of the variational autoencoders telling that normal distribution is somehow not very nice for the task because it is in higher dimensions, it is too concentrated. So in 2 dimensions, it looks like, okay, slowly fading away, but in higher dimensions, they argue that the mass is very concentrated in a very small ball, and then it fades away very quickly. And so it in practice there could be more suitable choices, or if you say that, okay, I know my data is actually consists of several mixtures of different objects, and I would really like to see in the latent space that for one kind of objects, all the latent encodings are here, and for other type of objects, all the latents are separate away. And then you could use some appropriate, maybe you could even, so if you are interested in the latent representations that have this property, then you can do additional design steps how to facilitate this, right? But what we are saying at this point is that, okay, so this is kind of general scheme that you could just take any fixed noise space and learn an arbitrary distribution from that. But then if you're not happy with this, maybe you could think of learnable distribution in this space. But then
There you show it, it's possible to use the others, so it's just like probably it's general. It's like asking if there is like some advantage of using other. You say maybe sometimes yes, it was good.
oh, why I took the uniform? No, because yeah, this is
this is just transformation, general transformation of one
mm.
distribution to another distribution. There you show normal distribution, but there could be other.
Well, for sure we can map from the normal, right, to logistic also. So the question is how to learn such a mapping, and there are several approaches, and for all of these approaches somehow what we need is that to address this question, so we have the data represented by these data samples and the distribution represented by these dots only. Then how do we sort of measure the difference between the data distribution and our model distribution? And one way to measure this difference is this forward callback-Leiber divergence. So if you have callback-Leiber divergence PQ, and that this is gonna be like expectation, and P are our data, right? Here, so the expectation over data, and then there will be log Q x minus log P of x. And in principle, so if you fit in the model Q and it is some parametric mapping, like parameterized by parameters theta, then we already know this. So this is what we've been doing all the time. So this is like expectation over data of the log likelihood, negative log likelihood under our model of the data. So this would work. So then the callback-Leiber divergence, to optimize it, to approximate it with the Q, it works even without having the density of the true data. We just suffice to sample from the true data, and this we have as a training set. And what we need is to really just to be able to evaluate this likelihood. But if you have only this model with this decoder, it is still a problem. Like, look, so if we are, okay, so we are fitting P theta. Let me make it like more consistent. So P theta, and this is P star. So to evaluate this log likelihood of P theta, it means what? We need kind of, for any given data point, we need to map it back, so to see where it comes from this latent space, then pull the density at that point in the latent space. And also, so this is the density at that point at latent space. And also because this decoder, it can squash or stretch the space, we can need to compensate how the density stretches under this transformation. So there occurs this determinant Jacobian of this mapping. Yeah. And then this looks a little bit complicated, and this is not the way we're gonna take, but it is a possible way. So to make this way feasible in practice, what we need is an invertible mapping here for the decoder. So the decoder must be invertible, and its determinant Jacobian must be tractable somehow. So this is possible with these invertible neural networks, which are designed in such a way that every layer is invertible by design, and also is simple enough such that we could compute this determinant Jacobian not but not too much computational effort. And this gives you a variant of generative models that's called normalizing flow models, or what is it? Non-volume preserving flow models. Yeah, anyway. So that would be one approach, this normalizing flow models. And it has these limitations, right? Like by requiring the network to be invertible, then the spaces must have the same dimension, right? And the flexibility of the network, which must be invertible by design, could be rather limited. And this additional constraint that this must be tractable also limits this architecture a little bit. It's possible they could learn quite general things and even generate complex distributions, but it is limited from this modeling perspective. So what we're gonna do is to relax this condition a little bit, that there is a strict one-to-one correspondence between the latent space and the image space. And this now we are coming closer to variational autoencoders. We will accept of this latent space distribution. We will consider also, so the decoder will be kind of a mapping. So it will consist of a mapping that takes the input latent code and sends it to the target space, but also adds like a Gaussian distribution on top. So this is what this model says. We take the mapping, the deterministic mapping of the latent, and add a little Gaussian on top. So here this red thing. So the noise is now injected twice in this model, like on the input, if you want to generate, I mean. So if you first generate a random point here from standard normal distribution, then map it here, and then add a little bit noise to the output. Okay, so this is going to be our decoder. So the sampling process is two steps. So first sample the prior and then sample from this normal. And then the kind of this distribution, the target distribution in this space is covered as a mixture of these little Gaussians, right? And now this generative process, it induces in the target space this distribution, which is kind of, so we need to take these little Gaussians and look at the expected value over all of the possible latent codes. So then if you ask the question, what is the density of at a particular point in this space, we kind of need to evaluate the logarithm of this expectation. And this would still be difficult, but there will be a workaround. And the workaround, it employs also design an encoder. So what is an encoder? It is a kind of probabilistic equivalent of the inverse mapping. It will tell that, okay, so for any given image, to tell what is the distribution of the latent space codes which are likely to generate that image. So technically we want this encoder to approximate the true posterior distribution of the decoder. Are you clear with what is the posterior distribution means in this context? If we have P of Z and P theta xz, so then what is P theta Z given x? So we have like prior distribution. This is our observation model. And then this defines somehow some joint distribution, right? So then this defines kind of joint distribution of z and x, which will be p theta xz pz. And then, according to this joint distribution, we could ask the question, okay, so what is the conditional distribution of z if the x is known? Right, so that's going to be given by the Bayesian formula. So it will be this p theta zx so the posterior is itself kind of hard to compute because it involves this summation or integration over the latent space. But we will learn to approximate it. And now suppose you have it. So suppose we have such an encoder or the inference model that allows for a latent code for a given image to tell what is the distribution in the latent space that of codes that could have generated this image or them. Suppose we have it. And then it turns out that the likelihood of this decoder, it then can be expressed in such a form so that we will see it later, like the derivation, how we come to this. But now on the level of the idea, so it will be expressed in the form that everything here sort of consists of the components that we have. So we have this conditional model. We can evaluate this likelihood because it's Gaussian. We have this prior, it's also Gaussian. We can sample from this encoder. So here, this is expectation over this encoder. And here is the log likelihood of the encoder. So if we are optimizing over the decoder, this does not matter very much. If we are then fitting the encoder, we will need to model this somehow such that this log density of the encoder must be also tractable. Right, so it kind of allows us to circumvent this problem of inverting, of invertible mapping. So this decoder and encoder, they don't need to be like invertibles in the sense that several latent codes could map to the same image or to very similar images, or the other way around. So several images could correspond to several latent codes. So this probabilistic description or the dimensionalities of these spaces need not match. So this probabilistic model bypasses all these limitations of an invertible mapping. But of course, we still have like unresolved questions. Okay, how are we actually going to learn such a pair of decoder and encoder? Any questions to here? All right. Now, so actually, then how this is where this is coming from, and how this encoder emerges. In principle, it emerges as a kind of auxiliary tool. So basically, the goal was to here we have defined the model. So we have defined our generative model in this way, and there was only the decoder and this latent distribution necessarily to define this model. But the encoder, it comes as an auxiliary tool. And it comes from the following approach. So suppose this is our data evidence. So this is like log likelihood of all our training data indexed by I. This is what we want to maximize. So you could like maximize the likelihood of observed data, so that would correspond to this forward callback reliable divergence between, so from the model to the data distribution. But now this P of X, it's complex, right? So for any image, there could be multiple explanations, multiple latent codes with this prior distribution and then the conditional distribution to generate that X. So we have this term which is a sum over the latent representations okay, if it's a continuous space, it is an integral, and that's usually interactable. And what works is that we have logarithm of this expectation or the sum. So we cannot readily make a stochastic gradient estimate of this thing. So if it was not this logarithm here, it would be easy, right? We would just sample a data point, we sample n z, maybe from the prior, and then the pp of x would be our stochastic estimate of this double sum, and we could differentiate that. But there is this logarithm, and so we cannot just get rid of this summation by replacing it by stochastically by samples. So we need to do something with that. It would be really nice to somehow, if you could swap this summation and the logarithm. And in a way we can by employing this encoder. So technically it works as follows. So here we divide and multiply by this conditional distribution of z given xi. So this, obviously this cancels, right? And then by the same lower bound inequality as the Jensen's inequality, as the inequality that we used for Kolbe-Kleiber divergence, it could be rewritten in this form, where you have now like sum over z, and then this density as a weight factor, and then logarithm of something, right? So we swapped actually sum and logarithm, but what appeared is this Q distribution here and here as a result of this. And like here, what you see here is logarithm of the expected value, right? So the logarithm of the convex combination of these things, and the Q is the convex combination coefficients. And on the right-hand side, you see a convex combination of the logarithm. So you do recognize the same like Jensen's inequality for the logarithm. But we could also prove this inequality using what we already proved for the Kolbe-Kleiber divergence. And this will give us like a nice equivalent way to view in this lower bound, actually. So what I have here is this log likelihood, which is often called evidence, and I subtract from it this lower bound, which is called the evidence lower bound, and let's see what is this difference. So if this difference is non-negative, then this inequality holds, right? And yeah, okay, so there's like few technical steps to do this, which show that this difference can be rewritten as the Kolbe-Kleiber divergence between this Q distribution, which we put here like arbitrarily, so this inequality holds for any Q distribution. But we show that the difference between our likelihood objective and this lower bound, this kind of approximate thing that we will be able to optimize, the gap between them, the difference between them is actually exactly the Kolbe-Kleiber divergence between this Q distribution and the true posterior. So if this Q distribution matches the true posterior, so if it can do well this probabilistic inversion, then the inequality becomes equality, and so there is no gap. So our goal will be, okay, to actually have this learn the posterior. Any questions so far?
So the core idea is that you learn the encoder as the backward minimization of the KL divergence, right?
In effect, yes, but we will see that it is even simpler than that, so that you will not need to optimize this explicitly. So but it is the interpretation.
It looks like the EM.
Yeah, it is. So we have this lower bound, and if we express this ratio under the logarithm as the difference of logarithms, we can separate it into terms. So one term will depend on the this conditional likelihood under our generative model only. And this looks, so this looks pretty much as the likelihood that we optimize when we learn conditional models, right? So you have some samples of images, and then we have corresponding latent codes according to the encoder distribution. And then what we want to maybe fit the decoder. So the decoder must then learn to approximate x given z. So this looks like data fitness, or it's called data fitness part, and it looks like essentially if the encoder is fixed and we want to refine the decoder only, then we are in the setup of supervised learning, so that we are given some pairs of x and z, and we want to fit this conditional model, right? So this we already know how to do. And the second part, it is p of z grouped together with this q of z given xi, and then so this part together. So this results in the Kullback divergence, Kullback-Leibler divergence between the q, this our encoder, and the prior model. Basically what it does, it tells that, okay, if in encoding of every point, its Gaussian distribution is encouraged to be closer to our whole prior distribution. So it's kind of ballooning the encoder distribution, forcing it to have larger variance, if you like. So increasing the entropy of this encoder distribution. Sorry, I'm referring to this part. So this is like divergence between our encoder and the prior. And so it has the interpretation as a kind of regularizer that a priori tells that the encodings must not collapse to single points, so they must have high entropy. And then, yes, optimizing this evidence lower bound, then we could consider it maybe first as alternating optimization, and this reveals us connections to the EM. So if we fix the encoder and optimize in the decoder in parameter theta, then it's what we said. So this part is not relevant, and in this part, it's like supervised learning. So we complete the data by the encoder, and then learn the decoder as it was supervised training. And then this would be the maximization step of EM, right? And then the expectation step of the EM would be for the current decoder to refit the encoder. And refitting the encoder means maximizing this lower bound with respect to the encoder. And in the EM, you would like straight away replace, so you would say, okay, the encoder must be the true posterior, and you just compute the true posterior. But here we cannot compute the true posterior, so we should somehow try to fit this true posterior. The useful interpretation of this alternative maximization in the decoder and the encoder is the following. So suppose this green line is our likelihood function, and the lower bound is this blur scene. So for any choice of this Q, for any choice of the encoder, we have a lower bound, right? And then if we have some lower bound and try to improve it in theta, then we are getting, what we are obtaining is a higher value of the lower bound, but it's not necessarily that we are obtaining a higher value of the likelihood, because this lower bound could be loose, right? So if this lower bound is, so this is a lower bound as well, right? That's not good. So we want this lower bound to be as tight as possible, and the tightest lower bound is given when this Q distribution is the true posterior. And then it touches the likelihood, then there is this equality right here. And the derivatives coincide, so this could be also verified. So up to the first order, it is approximation of the true likelihood. And at the same time, it is the lower bound on the likelihood. So then you are guaranteed, if you optimize the decoder, so if you optimize this lower bound, then we are guaranteed to improve also the likelihood. But this will be only true if this lower bound is tight here. So in the EM, the rationale is that, okay, we gotta make it tight at every iteration. So that's like a common expectation maximization. But in variational autoencoders, we're not gonna do this, so we will take a little bit other perspective. So we will do small steps of improving in both the decoder and encoder, and even actually simultaneously. And this would make sense as well. But before we go into that, so let's see what the optimization in the encoder would be doing. So in practice, we will optimize the same expression with respect to the Q distribution, with respect to the encoder. But because of this derivation, because we showed that this difference between evidence and lower bound is the Kolbe-Kleber divergence, it is actually equivalent to say we're gonna optimize this, or we will be in effect optimizing that. So we will be optimizing this. This will be tractable for stochastic optimization. We will see. And okay. Sorry, not only this regularizer, but this whole thing together, because Q is also here. So it is important to optimize in Q all of that. But we know this is actually equivalent to optimizing just this reverse Kolbe-Kleber divergence from P to Q by this result that we've proven. So in fact, that we know that optimizing this lower bound in the Q distribution, tightening this lower bound with respect to the Q distribution, is in fact identical to fitting the Q to the true posterior in terms of reverse Kolbe-Kleber divergence. So we cannot compute this true posterior distribution. We will not compute it. But the result of the optimization will optimize this reverse Kolbe divergence from the encoder to the true posterior. So it will learn to do the Bayesian inference as a result. Does it make sense? Why Bayesian inference? So this is like if you have, okay, I mean, if you don't, never mind. So we have this mapping, right? And by sampling many points here, we sample many Gaussians here, and it defines some distribution, right? Not necessarily our data distribution, but it defines some distribution. Here's my red chalk. The question is, given a point here, what is the distribution in this latent space of codes which could have generated this point? So this is the posterior distribution. And what I'm saying is that by design of this lower bound, like optimizing it in the encoder parameters, E is equivalent to fit in this distribution with Q in the reverse Kullback-Leibler divergence.
Maybe I'll ask, I don't know if everybody understands it, but like suddenly like from equation 1 to equation 2, you basically substituted a priori probability on Z with the supposed probability.
I did not. I used this identity that the difference between elbow and evidence is this divergence. So it is. So this is evidence, this is elbow, this is divergence, and here this is elbow is evidence minus divergence. Now in the expectation over the data, everything.
Like, to be honest, I'm completely lost like in all the equations, but could you maybe explain like
yeah.
like the principle in general, like without details, like how we train both the encoder and the decoder like at the same time to approximate. Like
How? Yeah.
Like, I didn't like there was a lot of equations, but to be honest, I didn't understand like
Yeah.
the core idea in the beginning.
Yeah, that's all right. And actually, we are not there yet. So I'm not telling you yet how to optimize them together. I'm telling you what it will do. Right. And now about how. So sort of the other view. So we say that we could maybe, like if someone knows expectation maximization, then it's a good connection point. Then from that perspective, we would kind of alternatively optimize in the decoder and then optimize in the encoder, and then this corresponds to EM or the variational variant of the EM. But in fact, what we're gonna do, because we have this lower bound, we just will go and jointly optimize it in simultaneously in the both decoder and encoder, and we will be doing just even maybe small steps and the stochastic gradient steps. So because we have this lower bound and the evidence, and it is kind of, it holds globally, so this was one view, right? So tightening the lower bound and then maximizing it. And the other view was, okay, we'll just kind of improve the lower bound, a little bit, then optimize the current lower bound, improve it a little bit, optimize it a little bit. So in this picture, there are kind of multiple lower bounds depending on the current point. In this picture, this is viewed as a lower bound in these two parameters in both theta and q. And then this is sort of a function that we will be globally optimizing in both in theta and q. So we will achieve what we wanted in the previous slide by just joint optimization of this in the theta and q. And to do this in practice, what we need is we need to model this encoder somehow. And like in the Gaussian VAEs, the design is that the encoder will also be a Gaussian with the mean and variances learned by some neural network. So we will have a neural network with several layers, and in the last layer, maybe this part of the output will be considered the mean parameters. And this part, maybe if you have some linear layer here, right, this could be positive or negative, so we need to make it positive, so we could somehow map it through, let's say, soft plus. Or the exponential mapping, right? Whatever. And this will give us the standard deviation or variance parameters. So we designed some neural network that outputs means and variances per coordinate, and then this is going to be our encoder. So this is the model in practice. Of course, it cannot model like arbitrary shape distributions, so it will be a limitation from this design, but everything will become like easier for us to compute. So if we model the encoder in this way, then what we can observe is that this callback library diverges to the prior. It can be computed in closed form because this encoder here, so the prior is Gaussian, and the encoder is Gaussian, and then callback library divergence between the factorizing Gaussians over factorizing over the coordinates. I mean, so this is like so the encoder, our encoder cannot model this like skewed Gaussian distributions because we have here this diagonal form, and if they are both sort of spherical, then the callback library divergence is easy to compute. And we should do this either at the seminar or at the labs, yeah, because you will need it for the lab. And okay, so what remains, I mean, in terms of how this is gonna work in practice, what remains is to stochastically estimate gradients of these two expressions. So for this expression, everything is fine. We have analytic form for this callback library divergence, and this is the data distribution. So we will just have stochastic gradients by differentiating this closed form callback library divergence in Q when we need. Then really what remains to see is the kind of how do we compute gradients of these data fitness terms. But we need gradients in both, in the decoder, in theta, and in the distribution Q. So let's put it on the new slide. So we have this evidence lower bound. And the gradient of this data evidence part in theta is fine. So it is like we said, it is like supervised learning. So we just complete the training sample X by the latent codes Z generated from the current encoder. And then we just need to differentiate the log likelihood of the decoder in theta. So we could just, we could interchange this differentiation and this expectation, which means we could just sample one latent code from the encoder, a random latent code from the encoder, and then for that latent code, kind of evaluate the decoder and look at this little Gaussian density of the decoder for our target training sample we started from, right? So this is what this first thing says. Now for the gradient with respect to the encoder parameters, this is a little bit more complex, right? So we have the dependence on the parameters here in the expectation. And this is the difficulty, because we cannot now easily just swap this expectation that depends on the parameters with the gradient in that parameters. So that's not legal, right, to do such interchange. And which is the same as to say that we cannot just sample from the encoder and then take the gradient inside, because this sample from the encoder depends on the parameters. So what we need to do is, okay, so maybe it's not the only way how to estimate this gradient, but in this case it is sort of the way, and it's called the reparameterization trick. Now, the normal distribution from our encoder, so this blue distribution here, we could generate it, or we could represent sampling. So this expectation we can represent as sampling from just standard normal distribution, but shifted and scaled with the parameters of the encoder. And now these parameters of the encoder, of course, depends. Sorry, so these are outputs of the encoder, mean and sigma, and they are depends on the parameters of this neural network constructing them. So this is somewhere all the 5 weights are sitting. So if you do this reparameterization, then like this expectation with respect to the encoder, we could write as the expectation with respect to just standard normal distribution, but then remapped, right? So we sample this noise and then transform it. And then if we do this, now we can swap this gradient and this expectation. And so we will obtain this expression. So what it tells us is that, okay, you could just sample random epsilon and then compute the chain rules through the decoder of the stochastically encoded, basically stochastic sample. I think this we will also need to detail somewhere, maybe in the lab or in the seminar.
Yeah, I don't know. Maybe this is like when you see the equations, I think this is like obvious that you can do it. Main advantage is like that it allows you to do the gradient and then everything suddenly functions. Good. Now you can compute both variants. So you can do both steps. The particular descent easily. Now you just iterate these 2 steps.
Yeah, so the key step was this evidence lower bound with this stochastic encoder and decoder. And then the estimating these gradients is done, yeah, so something technical. You need to look at the details, but kind of possible. Shall we go on? So what it will be overall, how this relational encoder is learned, it's pretty simple. So we sample a mini batch of training data, we apply the encoder network to get the mean and variance parameters. We compute callback-label divergence between the distribution of this encoded of the encoder and the prior.
It was close for that.
Yes, it was close for, yes. Then we just sample latence from the encoder, but using this reparameterization trick that we discussed, just so such that this, in effect, this sample could be differentiated through. And then we apply the decoder network on these random Latin codes and compute the log evidence. So basically, we used the encoder in several times. Once to compute this prior, once to complete the data, to sample this latence that we do not observe, and then it's kind of supervised learning, like log likelihood of the decoder using this completed data. But we also differentiate that through the encoder parameters, and this is possible thanks to this reparameterization trick. And so we could just make a joint stochastic gradient descent step on both parameters at the same time, on this theta and phi. So basically we just compute, what it says is that we are computing this, where we sample from the training distribution and we sample from the encoder, and we do backpropagation and automatic differentiation. Only when sampling from the encoder, we have to use this reparameterization trick, or otherwise the gradient will not do the right thing for training the encoder. Yeah. 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 No, it matters. This is because in the previous year it was 2 lectures on stochastic relational inference and autoencoders, and this is now compressed into one. Yeah, the decoder. The decoder, yes, we said we're gonna use what? The decoder distribution with some variance, and it could be either a fixed small noise variance, which is a hyperparameter, or it could be learned parameter, and both choices are suboptimal. So if we have it fixed, then it is somehow a limitation, right? So we have this constant blurring thing. If we make it learnable, it could be becoming very small, and then we have a vanishing gradient problem. So it might be a little bit difficult to learn it correctly. Anyway, so in practice, so the kind of recipe to optimize is simple. In theory, in practice, there are many different caveats which need to be circumvented. So these architectures of this encoder and decoder must be appropriate. And that could be local optima because it is nonlinear encoder and decoder, and of course this optimization can be getting stuck in the local optima. And some of these local optima tend to be corresponding to what is called the posterior collapse problem with these relational encoders. That some of this, so the encoder is the Gaussian distribution over all of our latent dimensions. And sometimes it turns out that some of these dimensions, some of these Gaussians, are matching exactly to the prior distribution. We see here this regularizer that attracts this encoder to the full prior, and then what happens is that for some of the dimensions it is perfectly matching to the prior, so it is kind of over-optimizing this regularizer. And this could be from one theoretical point of view, it is actually a feature, so it is kind of automatic dimensionality reduction. So it selects how many latent dimensions are useful for this model to represent the data. On the other hand, it tends also to occur as a kind of local optima, so such that much more dimensions are collapsed than would be really best to represent the data. And for that, maybe some care needs to be taken how this encoder and decoder are initialized, or how fast the encoder is like balancing the learning rate of the encoder versus the decoder, such that this doesn't happen. Yes, and one more limitation, it comes from this, so from this design that we said, okay, our encoder is going to be a Gaussian distribution here. If we do this, then it cannot fit the true posterior degree distribution. If it cannot fit the true posterior distribution, there is necessarily a gap between this lower bound and the likelihood. And if there is this gap, then we are not truly optimizing the likelihood. So it is not best possible fit of the decoder to the target data in the family of the decoders. So somehow the decoder must seek a compromise between fitting the target distribution and having a simple posterior that can be easily approximated. And okay, so it is some trade-offs in practice, right? So you need to balance this and balance that. But there is a range of models and hyperparameters for which these things work as we would like, and we can learn some latent representations where, in particular, if you look at this MNIST data, that was the example before, and some bilinear interpolation in the latent space of these MNIST digits, then reconstructing, we are reconstructing sort of maybe this is not the best image to show. I was making this a bit quicker. You can see, like if you could transit in the style from one digit to the other digits, like bold, some dimensions would correspond to the boldness of these characters, some dimensions would correspond to sort of style, then the interpolation between different digits, like 3, interpolating between 3 and 1 goes nicely through these 2s. So this latent space that it found has smoother and more captures like more useful structure than would be achieved with plain autoencoders. And yes, and we have the possibility to generate new digits, and we have the possibility to also like estimate the likelihood of any data point in this model. So it's kind of now probabilistic everything. Yeah, so we run out of time. I mean, I'll just say a few words what is remained on the site. Then the story was, okay, this was our model so far. We had this latent distribution and target distribution where we've been adding a little bit of noise. Now the next variant of the model would be to maybe start from some latent distribution, add a little bit of noise, like, and then add a little bit more of noise, and then add a little bit more of noise, and then add a little bit more of noise, and this is our target distribution. And if we do this kind of generator, we could also introduce a corresponding encoders. So, and the encoder could be like this. Or in principle, the encoder doesn't have to go in this factorization, because so if you have the data point, in principle what we could do also is that the encoder could say, okay, we will just straight away estimate the posterior in this latent space, and these posteriors, which we also will need, we will then somehow estimate like this. And so this is the kind of another variant called ladder VE, which works better in practice because somehow the encoder, so the design and the architecture of this is such that it is easier to capture the true posterior if it is designed in that way. And yeah, so then everything is tractable. This evidence lower bound it consists of this many terms, and everything is optimizable. And these were kind of the best results people were getting with this hierarchical relational autoencoders. So then, like maybe the last bit to the story was that if you look at the diffusion model, we also find out that there is such a chain in the generator where at each step we are using some unit, and the training principle is sort of similar. There is this evidence lower bound applied, and there is the encoder. The only funny thing is that the encoder has no parameters. So the encoder here is just so what is the equation for the encoder? So the encoder is only this. So it consists of just shrinking the input and adding some noise to the input. So the encoder is kind of simple by design, and it is the diffusion process. So diffusion is everything blurs away. So if you apply this diffusion process, it just transforms everything to a normal distribution, right? So if you just, okay, the scale here, the shrinking here is needed to make the limiting distribution a normal distribution, right? So it does not grow or contract. So the encoder blurs everything to the normal distribution, and the decoder is somehow is a neural network parameterized process that at every step kind of tries to denoise, if you like, the image, but not only. So the decoder is also stochastic. So at every step it generates something, like progressively. So there is now not so much of the interpretation of this latent space, because the latent representations consist of this and also the noises that we've been generating in all of these steps. But the fact that we are using these little Gaussian steps at every step, it overcomes these limitations. So it overcomes the limitations that we discussed, that, okay, we cannot match the true posterior, we cannot approximate this well. So this design of making many little steps with these Gaussians, it actually overcomes this limitation. And now, despite that, the fact that there is not so much nice interpretable latent space anymore, but the generation is kind of learning, and generation is much better, right? So you know, the diffusion models are now the best, right? Okay, so let's finish with that. Thank you for your patience.
Maybe just a small suggestion. I don't know about the presentation.
Okay.
Potentially, I'm not sure. But at least for me, it would make more sense if slide 16 first appeared before all the math heavy parts, let's say. And there was some sort of explanation of the overall process while making a lot of assumptions, let's just assume we can do this, and then explain how it is done. Because for me it felt a bit like, okay, we're going somewhere, but why are we going there? You know?
Yeah.
That would be my preference, but I'm not saying that that's the right way to do it. It's just
Yeah, in general, it's not my favorite approach when first the algorithm is presented and then we are trying to explain what it is doing. I like to sort of introduce the goals, how then we derive stuff, and then we end up with some algorithm.
Yeah, well, maybe I didn't understand the goals. But maybe it was just my problem.
Okay, but thanks anyway.
Seminar, and only then you can probably understand. I don't think there's, I have
Okay, so this was the most loaded lecture of the course, then with the most mass, and I really hope that the details you will catch up on during the practicals. So see you tomorrow at the lab on this topic.